Hello, this video is going to talk about magnetic fields. Students will be able to recite the equation for magnetic force and explain the right-hand rules for determining the direction of magnetic forces and fields. So a wire carrying a current in the presence of a magnetic field will actually feel a force. The wire will actually move based on the amount of current flowing in the wire and the strength of the magnetic field around the wire. This relates to the Lorentz force law, which says that the force acting on something, like on a current, is equal to the charge times the velocity of the charge in the wire times the strength of the magnetic field, which is B, times this sine theta thing, which we're actually not going to use very often. So B stands for the magnetic field measured in the unit Tesla, capital T, named after Nikola Tesla. And 1 Tesla is the same thing as a Newton per amp meter. Q stands for charge, like it has in this whole unit, measured in coulombs. V is velocity, just like it was in kinematics, measured in meters per second. And F stands for force, measured in newtons, like every force has been. And the theta in the equation only matters when the direction of the charge's motion and the direction of the magnetic field are not perpendicular, which they usually will be, so we're not going to really need that sine theta part very often. Another equation that relates to this stuff is F equals ILB sine theta. In this equation, F is still force, I stands for current, measured in amps, like it has. L stands for length, measured in meters, that's how long the wire is. B still stands for the magnetic field strength, which is measured in Tesla. And just like before, the theta is the angle between the current's flow and the direction of the magnetic field. In most situations, these will be perpendicular to each other, which negates the sine theta part of the equation altogether. So usually it'll just be F equals ILB, force equals current times length times the magnetic field strength. So to determine the direction that the wire feels a force, we're going to use the right-hand rule. In this case, it's called right-hand rule number 1. This rule states that if your thumb is pointing in the direction of the current flow, or the velocity of the charges, and your 4 fingers sticking out, pointing in the direction of the magnetic field, then your palm will point in the direction of the force. And we call it the right-hand rule because you have to use your right hand for it. If you use your left-hand rule for this rule, you'll end up with the wrong answer. It'll be the exact opposite, which doesn't work. Hans Christian Ørsted in 1820 discovered that when he connected a wire to a battery so that a current was produced, a nearby compass shifted which way it was pointed, which he thought was kind of strange. He hadn't seen that before. He just happened to have a compass sitting there. As a result, he started to figure out that a current carrying wire creates its own magnetic field and that they're very much related. He also found that the direction of the magnetic field around his wire depends on the direction the current is flowing. So, if, as shown in the picture here, the direction of the magnetic field around a current carrying wire will be in the direction that your fingers curl when grasping the wire in your right hand with your thumb pointing in the direction of the current's flow. Like in the first picture here, if the current's flowing up this wire, you imagine grabbing it with your right hand with your thumb pointing up, the fingers would curl like this. Same thing here. This is called right-hand rule number 2. That's it for this video. Remember to use your notes to answer the questions in Schoology and bring your notes with you to class.